Okay, guys, we'll start now. Check. I'll give you a complete overview of the biomolecules topic today. So if you have any doubts, you can stop me and ask. Okay. Check. For biomolecules, the basic definition is it should be, uh, you know, polyhydroxyaldehydes are ketones, and that should be, and polyhydroxyaldehydes are ketones that should be optically active. So remember these wordings mainly. This one and compounds are optically active. These two are the main definitions for carbohydrates. Polyhydroxyaldehydes are ketones which are chiral and optically active. Okay. By classification, carbohydrates can be monosaccharides, oligosaccharides, or polysaccharides. Monosaccharide means single unit which cannot be further hydrolyzed. Oligosaccharide is 2 to 10 units. Polysaccharides is more than 10 units. Glucose, fructose, galactose, mannose, ribose, all these are examples of monosaccharides. Sucrose, maltose, lactose are for disaccharides. Starch, cellulose, gums, resins, etc. These are all polysaccharides. Okay. If we have carbohydrate which is made up of aldehydes, then those are called aldoses. So anything which we have ribose, threose, erythrose, mannose, allose, glucose, these are all aldose family. Ketos are the ones which will have a keto family. So we'll have keto, triose, tetrose, pentose, hexose, and so on. Okay. Next, based on basis of the carbon atoms in a hydrolyzed product. So if we have three carbons, we call it as triose. Four is tetrose, pentose, hexose, lactose for seven. Okay. If it is aldose, if it is aldehyde group, then it is aldo, triose, and so on. And similarly, if it is keto, polyose, and so on. If you know that for making a monosaccharide, we need to have generally 3 to 7 carbons at least. Okay? That is a requirement. Minimum is 3, maximum we can see up to 7. The most basic uh, sugar is D-glyceraldehyde, where we have OH on the right hand side. That makes it as D. Okay. Then we have dihydroxyacetone, which is for keto cases. So 3 in case of keto and 3 in case of aldehyde. Okay? But here you notice that this does not have an optically active carbon. Correct? Optically active carbon is not there. So this is not the simplest carbohydrate. This is a carbohydrate. This is the simplest ketose, but not necessarily a carbohydrate form. Okay. Next, most naturally occurring monosaccharides. Okay, pentose is D-ribose, which is present as RNA, deoxyribose. Then we have in hexoses D-glucose, mannose, allose, galactose, and fructose. These are the ones which are most available form. Okay. The other day we discussed ribose, all three OH will be on the right. Deoxyribose, instead of this OH, we will have H only. Okay, that is deoxyribose. Now you see the family tree. First glyceraldehyde, as you extend the carbons, we will get erythrose and threose. We discuss how the structure look like. Then from erythrose, we will get ribose and arabinose. This also we discussed. And from ribose, we will get altrose and allose. And arabinose, we will get glucose, mannose. And from the rest of them, lixose and xylose, we will get galactose and so on. The marked ones, ribose, arabinose, glucose, mannose, and galactose. These are important ones for us. Okay. So please make sure that you are aware of these structures clearly. Yeah. Next. When it comes to aldohexose, there are 4 asymmetric carbons. Therefore, they have 16 optical isomers, out of which 8 are D form, 8 are L form. Okay. If you notice the D form, we have allose, aldose, glucose, and mannose. Okay. And glucose, idose, galactose, and thallose. Out of these, if you notice, 1, 2, 3, 4, as well as galactose and thallose, these are dextrorotating. This is important question again. How many D sugars of hexose are dextrorotated? How many are dextrorotatory? 1, 2, 3, 4, 5, 6. These are dextrorotatory. How many levorotatory? 2 of them are levorotatory. That is, glucose and idose are levorotatory. Rest all are dextrorotatory. Clear, guys? Next, check out If it comes to D-glucose, most of them are R configuration, R, and R, except on the third position, it is L configured. L here is sensing as S only. L here is same as sensing as S. Allos will have all of them has R configuration, right? Like this in mannose, we have 2 and 3 as S configuration. Galactose 3 and 4 as S configuration. Fructose 3 has S configuration. Okay. Now, when it comes to glucose in cyclic structure, because the minute you add glucose in an aqueous solution, most of the straight chain will convert into cyclic chain. And in a cyclic structure, we will have two forms, alpha D glucopyranose and beta D glucopyranose. Alpha D and gluco D are represented based on this case. Check where CH2OH and OH is lying with each other. If they are opposite, we usually call it as alpha. If they are adjacent, CH3OH and OH are adjacent, then we call it as beta. Then we call this as beta. So you can see this is alpha and this is beta. Clear on that? Next. If you say allos will also have the same form, alpha and beta here. Mannose will also have same form. This one you can see. These are opposite, these are adjacent. Fructose will also have same form. Now you can see CH2OH and OH are opposite. So alpha, CH2OH and OH are on the same side. So it is beta. Next, anodes. If you have carbon holding O with some group and OH, that is hemiacetal. If we have O and OR here, that is acetal carbon. Okay. If we have any acetal carbon on the sugars, we call that carbon center as anomeric carbon. We call that as anomeric carbon. Remember this word of carbon bonded with two oxygen atoms. That is called anomeric carbon. Okay. What are epimers? Diastereomers with more than one stereo center, but configurational changes only on one stereo center. If there is one stereo center other than anomeric carbon, if there is any change at one chiral center, it is called epimers. Erythrose and threose, these are both epimers of each other. D-glucose and D-galactose at carbon 4 are epimers. D-glucose, D-mannose at carbon 2 are epimers. And epimerism at these two is known. And at carbon third position, allos will be epimer. So one another important part you can remember is allos. Allos, all OH will be on the right hand side. It is just an expansion of ribose. Ribose, all OH will be on the right hand side with 5 carbons. Now it is with 6 carbons that will become allos. So glucose will be epimer with allos, with mannose, and with galactose. Clear everybody? Please make a note of that. Okay. Glucose is anomers with which of the following? Glucose is epimer with which of the following? Okay. Next. Sugars can be categorized as reducing and non-reducing. Reducing sugars includes the which can reduce Tollens, Fehling's, and Benedict solution. Which does not reduce these three, we call it as non-reducing. Should at least have one hemiacetal group. Here, it should have acetal linkages. Monosaccharide oligosaccharides except sucrose are generally reducing agent. All polysaccharides, including sucrose, are all non-reducing. Now, if you notice glucose, usually if you want sucrose to convert into glucose and fructose, either you do acidic hydrolysis or you use, uh, uh, catalyst, okay, enzyme catalyst. In this case, invertase. Invertase will also give you glucose and fructose. Glucose and fructose. And if you take starch, that starch can be first converted into maltose using diastase, another enzyme catalyst. And maltose can be converted into glucose using maltase. Okay. And glucose can also be further converted into ethanol using zymase. So I would request you to remember these: invertase, diastase, maltase, and zymase. And what is their role? Okay. Sucrose to glucose, invertase. Starch to maltose, diastase. Maltose to glucose, maltase. Glucose to ethanol, zymase. Okay. So remember these cases, guys. That's how we use the enzymes. If you notice an open chain and Fischer Haber projection, see this is an open chain of D-glucose. Now, within the molecule, we have an aldehyde group also as an alcohol group. And usually it will try to form a more stable ring. So fifth carbon onwards, this OH will start attacking on this carbon. As it attacks, this will become O minus and this H will be taken by this oxygen and that will convert into OH. And between this carbon and fifth carbon, we have an oxygen establishment and makes a chain. This is a five-membered ring. It's a five-membered ring. And because this is an sp2 carbon, OH could have come on the left, it could come on the right. Like this, here you can see OH is on the right, and here you can see OH is on the left. Okay. If OH is on the right, like most of the cases in the Fischer projection, we write OH on the right, that means alpha. If you write OH on the left, that means it is beta rotation. Okay. Now next note it. If you take this cyclic structure and write it in a planar form, if you show that cyclic structure in a planar form, that is called Haworth projection. And you see this is the Haworth projection. And for glucose, pyrene is a reference structure. Pyrene is a reference structure. So you can see this is the six-membered ring which you will write as a plane. And on top of them, at every carbon position, you will show that this carbon 1 is an anomeric carbon where it has formed hemiacetal. And if the OH is placed downwards, it is alpha. If the OH is placed upwards, it is beta. Yes, Vito. I'm audible? Can I repeat something? Pardon, I lost your connection. What?
The screen is structured.
Is it visible now? Is it moving?
No.